When chemical reactions occur, there's often some sort of a heat change involved, either heat being absorbed or heat being released. And we've seen examples of these in lab, where you mix two things and the temperature went down or the temperature went up. And so the words we use to describe those are exothermic and endothermic. Exothermic, the prefix exo, like exit, going out. These reactions emit thermal energy. Endothermic reactions absorb thermal energy. So the amount of energy released is of interest to chemists, and this can be quantified using an idea called enthalpy. Enthalpy is similar to energy. It's a specific type of energy. When we talk about the enthalpy of reaction, that's delta H reaction. Enthalpy is given the symbol H. I have no good explanation for that. Enthalpy is the amount of thermal energy or heat that flows when a reaction occurs at constant pressure. So basically, for the purposes of Chem 3A, we can think of enthalpy as being heat. If you go on to take 1A, you'll learn about there's a very subtle distinction between the two. So the sign of delta H is important. The sign gives us the information about which direction is the heat going. It's a lot like the sign of those transactions in your bank balance, right? If it says minus $10, that means that $10 left your account. If it's plus $100, it means that you made a deposit, you increased your balance by 100, right? So the sign convention for this enthalpy is exactly the same. Just remember that you have to think of yourself as the reaction. The reaction loses heat, the reaction gains heat. There's also the rest of the universe, the surroundings, and those are doing exactly the opposite. Because when money leaves your account, it goes somewhere, right? It doesn't just vanish into thin air. It goes somewhere. So it's positive for someone else, it's negative for you. So a reaction that has a negative enthalpy, a negative heat of reaction, the energy has left, but the energy has gone to something else. So an exothermic reaction, the reactants start out at a higher energy level, energy is released, and the products are at a lower energy level. So delta H reaction is negative. In an endothermic reaction, the reactants are low in energy, and the products are higher. It absorbs energy from the surroundings. Any questions? So delta H is negative for exothermic reactions because the energy is leaving. It's negative. So if we look at the combustion of methane, methane is the main component in natural gas. So when you turn on your gas stove, this is the chemical reaction that's occurring. The heat of reaction for this is negative 802.3 kilojoules. What this reaction tells us, this equation here with delta H, tells us that this amount of energy is released when 1 mole of methane burns. Because the amount of energy that's released is going to change based on how much methane you're burning, right? So think about maybe gasoline. So you have a teaspoon of gasoline and you burn that, or you have a tanker full of gasoline and you burn that. Not unlike that semi-truck did you hear about that? Like a week ago, crashed and burned a huge fire. The whole thing's on fire. There's a different amount of energy released, right? The more gas that burns, the more energy that is released. So by convention, when we give delta H, we say that this is the amount of energy for the amounts of each of these in moles. Because moles are more useful to us than numbers of atoms, because that would be too many, a big number. So 1 mole of this is going to release this amount of energy. 2 moles of oxygen When 1 mole of carbon dioxide is formed in this chemical reaction, this amount of energy is released. When 2 moles of water is formed, this amount of energy is released. So this becomes yet another conversion factor, where we can relate amount of energy to molar amounts of reactants or products. Delta H is positive for an endothermic because energy is coming in. The reaction of nitrogen and oxygen to form 2 no nitrogen monoxide, my favorite compound, is positive. So it absorbs energy. It absorbs 182.6 kilojoules of energy when 1 mole of this reacts, or when 1 mole of this reacts, when 2 moles of this is formed. So we have conversion factors that are very much like the mole ratios. So we could say that there's 182.6 kilojoules of energy per 1 mole of nitrogen that reacts. Okay? Amount of heat absorbed or emitted depends on the amounts. And we specify delta H in combination with a balanced chemical equation. So I've already gone over this, but it doesn't hurt to say it again. So the magnitude is for the stoichiometric amounts of reactants and products for the reaction as written. So if it is written with a fraction, if it is written with the coefficients not in the lowest form, you maybe note that, wow, that's not conventional, but it's just whatever the equation is written, that's what you go with. For the reaction as written, and it's for the molar amounts in the balanced chemical equation. So here is propane. This is the main component of LP gas, liquefied propane. So propane combusts with oxygen to form CO2 and water, and here is the energy involved. So 2,044 kilojoules are released, that's what the negative sign says, when 1 mole of propane burns. So we can construct ratios. Do it again. So if I wanted to know the relationship between moles of oxygen and amount of energy released, if I wanted moles of oxygen and kilojoules of energy, well, just like doing mole ratios, like if I was oxygen to CO2, I'd use 5 and 3. I'm going to use this 5 as moles of oxygen, and I'm going to use whatever this number is as energy. Now, the negative sign there is less important, but in some ways more confusing here. Just remember that the sign is just telling us the direction. So let's do an example. This is stoichiometry involving energy. So ammonia reacts with oxygen according to this equation. Calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. So I'm going to use my chemical equation to organize my information. 155 grams of ammonia. So I'm just going to write that amount here. And then what I'm asked for is heat in kilojoules. So I'll go over here and question mark kilojoules. So calculate the heat associated with the complete reaction. So our normal path for stoichiometry is grams to moles to grams, right? Hopefully that's been ingrained in your brain now. Grams to moles to grams. So here we are indeed starting with 155 grams. But we're not going to grams of product or grams of other reactant. We're going to kilojoules of energy. Because the heat of reaction applies to each of these in their molar amounts, 4 moles of this, 5 moles of that, etc. We don't need to do a mole-to-mole ratio here, and so this actually gets a little shorter. So we can skip this part, and we can go directly to kilojoules. Because we can relate this to any of these in moles. So all we have to do is get our 155 grams of ammonia to moles, and then we can go directly from moles of this to kilojoules. So 155 grams of NH3. This, I've got 2 arrows, I've got 2 conversion factors. So I'm going to go, no, that's where I started. Grams to moles, so moles of ammonia, and then I'm going to go directly to kilojoules. Same process applies here with dimensional analysis. Divide by grams of ammonia. Those cancel. Divide by moles of ammonia. Those cancel. So how do we go from grams of something to moles of the same something? Yeah, we have to add up the masses of nitrogen and 3 hydrogens to get the molar mass. So I'll spare us the details of that. It's 17.034. And then kilojoules to moles. This is all up here. Here this is negative 906 kilojoules. Negative 906 kilojoules. For how many moles of ammonia? 4. Okay? Just a new little twist. Then I get out my calculator. I've got 155 times the top, divide by the bottom, all the way across. So divide by 17.034 times negative 906 and divide by 4. So my calculator is giving me this mess. The unit would be kilojoules. It's the only one I didn't cross off. How many significant figures? 3. This number is 3, and this number has 3. That's a whole number. Doesn't mean it's an exact number. Kilojoules is a unit of measurement. Any measurement has uncertainty. The 4 here, is that exact? Yes, it is. The 4 is exact because exactly 4 molecules of ammonia will react with exactly 5 molecules of oxygen. This 4 goes back to counting of individual molecules, and that is exact. So 3 sig figs, and this is where we need to be careful in rounding and not lose our minds and say that 2,000 is the same as 200, because if I say it like that, everyone recognizes it's not the same, but you make it in kilojoules and people say it is. So this could be negative 2,100 kilojoules. Safer thing is to put it in scientific notation, because this doesn't specify the number of sig figs very well. Wait, let's just rewind. It would be 2060. See, I'm even having trouble with it. That's bad. 1, 2, 3. Or negative 2.06 times 10 to the 3rd kilojoules. That's a positive exponent because 2,000 is a big number. Any questions? Let me just say one more thing. I don't know if it's on a slide or not. I'll say it now. So here the question says associated with. Does that indicate a direction? Heat released or heat absorbed? It doesn't. So then the sign becomes important. So here, I better have that negative sign, because the negative sign tells me it's heat being released. This will mostly come up as an issue with mastering chemistry. You'll be frustrated because sometimes they want the minus sign and sometimes they don't. It's a little bit like, again, talking about money. If I say, well, how much did you spend on that fidget spinner? Are you going to say minus $10? No, you're going to say, I spent $10. Was that a debit from your overall worth? Sure it was. $10 went out. Why don't you say negative? Because we indicated it with a word, spent. So when the question has the direction in it, if this said, calculate the heat released by the complete reaction, then we would not want the negative sign. I will not intentionally trick you with that on an exam, okay? Did that one and we're on this one. Okay, so what mass of butane in grams is necessary to produce 1.5 times 10 to the third kilojoules of energy? What mass of carbon dioxide is produced? Now notice, this equation has a fractional coefficient in it. If I was asking you to balance this, I'd want you to multiply all of these by 2 and get rid of the fraction. Excuse me. But there are situations where this is appropriate, and this apparently is one of them. And so this amount of energy is released when 13 halves, or 7.5 moles of oxygen is burned. So we just deal with the moles that are given as the coefficients. So we want mass of butane, and we're given an amount of energy. So let's write this in here. So 1.5 times 10 to the third kilojoules. And the question is, what mass of butane in grams? So we should be able to figure out by process of elimination, if nothing else, that this is the butane. That's oxygen, that's carbon dioxide, that's water, so this must be the butane. So question mark, grams. So again, normal path is grams to moles to grams. But we're going to switch it up a little different this time. This time, they're asking us for grams, but instead of starting with grams, we're starting with kilojoules. Okay, kilojoules relates directly to moles of this, so we can cross off 2 terms when we're doing this. We don't need either of those. We're starting with kilojoules, and we're going directly to moles. So we can go kilojoules of energy directly to moles of butane and then to grams of butane. It's actually shorter. Well, 1.5 times 10 to the third kilojoules times, so we've got kilojoules to moles. Moles of what? Moles of butane. Moles of the thing we're interested in. There's no point in going to moles of something else and then moles of that to moles of that. You can get there, but extra steps is extra work and extra opportunities to make mistakes. So moles of butane, and then to grams of butane. So kilojoules come down here to cancel out. Moles come down here. So here's our kilojoules. Kilojoules, this many, minus 2658 for every 4 moles of that. So I put 4 moles in here, minus 2658. And I need the molar mass of butane. I'll do it up here, 4 times 12.01 plus 10 times 1.008 equals 4 times 12.01 plus 10 times 1.008, 58.12. So 58.12 grams of butane per every mole. So now I put in my numbers, 1.5 EE3 times 4 divided by negative 2658 times 58.12 equals, and my calculator tells me minus 131. This would have 2 sig figs, right? So I'm just going to add my 2 extras, and the unit is grams. And what is disturbing about that?
Negative mass.
How can you have a negative mass, right? You can't have negative mass. So what's going on here? So in the question here, what mass in grams is necessary to produce 1.5 kilojoules? Is 1.5 kilojoules released or absorbed by the reaction? It's released. So you've got choices with energy and stoichiometry and negative signs. You can ignore them and use your common sense at the end, or you can be very, very precise with them and you'll still be okay. So the precise thing is to say, well, this is energy produced. What I actually started with was a negative number. If I started with this amount of energy being released, then I'm going to end up with a positive mass, right? The other approach is to say, well, I'll deal with negative signs later. I'm just going to do this amount of energy. Which approach you take is up to you. This would be 130 grams, or 1.3 times 10 to the 2 grams. But negative mass is always wrong, in chemistry at least. I don't know about physics. They do things with antimatter. Any questions? Yes?
So you flipped the first sign from the last from the answer sign?
I put a negative on here because getting a negative mass alerted me to the fact that something's wrong with my signs. And I looked up here and I said, producing this much. Producing means giving off, that's actually a negative number. And then that takes care of my signs issue. Any other questions? Yes. Often in the homework, Mastering Chemistry, the absolute value of heat is requested and words are used to convey the sign. So if it says, calculate the amount of energy given off, you don't need to put a negative in there because you don't pay minus $10 for a fidget spinner. Yes?
For the rest, I should say something about CO2.
You're right. I didn't finish that problem. Thank you. This is actually one of my pet peeves when there's 2 questions and students only answer the first one. So I just did that. It happens. What mass of CO2 is produced? So that's going to require another calculation. It could be done several ways. You could take this mass and go grams of butane to moles of butane to moles of CO2 to grams of CO2, and that would be fine. Or we could just start with the energy, because that's only 2 steps instead of 3. So let's do that one. I'll do it in a different color so it's less confusing. So starting again with the negative 1.5 times 10 to the 3rd kilojoules, this time asking about CO2. I'm going to have moles of CO2 on top and the energy on the bottom. How many moles of CO2 are listed here? 4. So it's also 4. So that term actually ends up being almost identical. And then we need grams of CO2 to moles of CO2. 2. Okay, try that again. This would be the mass of carbon plus 2 times the mass of oxygen. It's 44.01. It scares me a little that I have that memorized. So if we go negative 1.5 EE3 times 4 divided by negative 2,658 times 44.01 equals, and again we're going to have two significant figures, so we're going to get 99 grams of CO2. Squished way down in the corner. Any questions? This is, I'm not going to test you on this, but this is useful to understand in lab. We've been talking about and doing calculations with combustion reactions. The amount of oxygen that is available when the reaction occurs is important. You've all heard of carbon monoxide poisoning. My family experienced carbon monoxide poisoning when I was younger. It's not fun. It was really, really bad. But we all lived. There was vomiting involved, though. So if there's not enough oxygen, let's go back and look at this combustion reaction. There's a particular amount of oxygen that's required to give CO2. If there's not enough oxygen, the combustion will still occur, but carbon monoxide is produced instead of carbon dioxide. And that's why cleaning the vents in gas-using appliances is really, really important. It has to have enough enough oxygen. So if we get a flame like this on our Bunsen burner, it's not getting enough oxygen. It's only getting the oxygen that's coming in right up here, and so we get a flame that looks a lot like a candle. It gives off more light, but it doesn't give off as much heat, and it also gives off a lot of soot. It will make the bottom of your crucible or whatever you're heating black, and that's messy. So as we increase the amount of air, we see the characteristic of the flame change. And this is what we would like. This is an optimum ratio of air to gas where we have a small inner blue cone and we hear that nice roaring sound. As with all things, you can have too much also. Too much air will cause your flame to float above the Bunsen burner. And the danger of this is any little breeze can extinguish it. And so that's not a good thing either. So this is what you're shooting for.